So that was the discrete logistic function, and we saw the sequence of bifurcations called a period doubling sequence as its route to chaos. I want to show you the same thing in the food chain model. You remember Z eats Y, and Y eats X, and you can think of this as wolf, sheep, and grass. And we saw the complex behavior, but it's the system. As we said, systems can display chaotic behavior, they can also display non-chaotic behavior, and they can display transitions between the two. So in the Hastings model, Z prime, Y prime, X prime, there's a bunch of parameters, A's and B's. And every one of those parameters produces a sequence of bifurcations as it's changed. But I want to take one particular one to demonstrate it to you. If you recall the X prime equation, the X prime equation, that is the grass, had logistic growth as its growth term, and then it had the predation term, and that of course should be a minus. The predation term of sheep eat grass is going to depend upon the number of sheep and the amount of grass, obviously. And we chose the form A1x over 1 plus B1y. And that means that the more X, the more can be eaten, and also the more Y there is going to be a crowding term that is going to prevent complete saturation. So if you think about this, let's think about this as A1 over 1 plus B1y times X. And this is the saturating predation function. And you remember that B1, and this is what we're going to use as our control parameter there. If B1 is low, then this function as a function of Y is going to look like this. It's going to saturate very fast. Whereas if B1 is high, then the same function as a function of Y is going to saturate much more slowly. And so our control parameter is going to be B1. So the first thing we see is we run a simulation with B1 at a very low value. And what you see is a stable equilibrium. It says that when this saturates very fast, the system goes to an equilibrium point, and that is a stable equilibrium point, or as we learn to call it, a point attractor. Now, if we increase B1, we get a bifurcation. And the bifurcation is to a stable limit cycle, to a limit cycle attractor. And that limit cycle attractor is a simple oscillation, and you see it right here. And so that is a bifurcation. In fact, that's a Hopf bifurcation, because a stable equilibrium point has become unstable and a stable limit cycle attractor has appeared. That is Hopf bifurcation. Now, if we increase B1 even further, you see that the simple closed loop of the oscillation becomes a doubled loop. And the doubled loop is a period 2 bifurcation from the original oscillation. So now we have this period 2, this doubled period 2 rhythm. If we increase B1 further, we get a period 4 oscillation, a more complex oscillation. And that more complex oscillation, as you see from the tracing, has a period roughly 4 times the original period. And then finally, as we increase B1 even further, the system undergoes a bifurcation to chaotic behavior. So there is a route to chaos in the food chain model. It goes through the same sequence of intermediate steps of equilibrium to oscillation, to complex oscillation, to chaos. And that is a frequently observed route to chaos in many systems, both mathematical and natural. And as a matter of fact, an example of this in a natural system, you can see the route to chaos in fluid turbulence exhibited really in this photograph, which is showing you on the extreme left-hand side equilibrium behavior. In the middle, you see the vortices that are characteristic of oscillatory behavior. And then on the right-hand side, there's a sudden transition to irregular and chaotic behavior. This can be reproduced in fluid experiments and has been in a beautiful sets of papers. I absolutely have to mention the names Golub and Swinney, who did a lot of these experiments. Golub and Swinney and a number of other physicists all carried out experiments in which they looked at the transition to turbulence in fluids under very carefully controlled conditions where they could control a critical parameter. I'm just going to show you a stylized version of the output. I want you to imagine a fluid, and the fluid is flowing in that direction. And we're going to put an obstacle in the path of that fluid. And I want to ask, what happens? Well, the parameter we're going to control is technically called the Reynolds number of the fluid. It's the parameter that governs the transition to turbulence. But the key component of the Reynolds number is just the velocity of the fluid. There are several others, but in particular, the velocity of the fluid. So first thing I want to consider is what happens to the fluid in the case when the velocity is very low. Well, in that case, the fluid flows completely in a laminar manner around the obstacle. It's called laminar flow because the flow stays in layers. A particle of fluid here stays at that level. For this very slow flow, the flow is actually symmetric front and back. And the system can be described as an equilibrium system. Now let's raise V a little bit. Here's our obstacle. Now we're going to get a new phenomenon. A bifurcation has occurred. And we're going to get a new phenomenon. And the new phenomenon is a pair of standing vortices behind the object. And you've seen this of an oar when you are rowing a boat. You'll see that pair of standing vortices behind the oar. So now it's no longer front-back symmetric. The back is different from the front. And this has a simple oscillation. And that oscillation has a frequency that we'll call F1. In other words, a Hopf bifurcation has taken place from an equilibrium system to an oscillatory system. And indeed, there is a Hopf bifurcation in the mathematics of the fluid flow equations. Okay, let's increase this a little more. And now the flow gets a little complex, because now what you see is a pair of vortices, yes, but they're no longer standing vortices. They're now peeling off top and bottom. So you get a peel off there and a peel off there and a peel off there and a peel off there. Meanwhile, the flow on the bottom is doing this. And vortices are alternately shedding, it's called vortex shedding, are alternately shedding top and bottom. And incidentally, therefore, the object is going to start to go into an oscillation itself. And so now there are two frequencies. The frequency of these oscillations, which is F1, but now there's also the frequency of the alternation of the pairing off of the top vortex, bottom vortex, top vortex, bottom vortex. And that is the second frequency, F2. Similarly, as you begin to increase V a little more, you can actually sometimes excite a third frequency. But if you increase the velocity substantially, now here is our obstacle, and here is our flow, and the flow behind the obstacle is fully turbulent. So the transition to turbulence in fluids is a route to chaos. The chaos can be documented in the turbulent regime. And this is clearly a parameter-dependent sequence of bifurcations as the system goes from the simplest possible behavior, equilibrium, to oscillation, to complex oscillation, to turbulence, which is chaos.